So if you're going to look at a truss, if you're going to analyze a truss, it's really important if you know whether each member is in tension or if it's a compression and by how much. So one of the methods that you can do is the method of joints. Another method is the method of sections. And so we'll talk about that in another video. But for method of joints, let's say that we've got this kind of a simple truss. Now, one of the things you'll notice, I need to put an external force on here to make it useful. Let's call this 500 newtons. So one of the things you'll notice about this truss is over here, it's pinned. And over here, it's a roller. Now this is really important because if they were both pinned, you'd actually have an indeterminate system. So that's indeterminate. It would be indeterminate if you had them both pinned. Because remember, if it's a pin, you have two reaction forces. Come here. If it's pinned, you have two reaction forces. You'll have a reaction force in the X and a reaction force in the Y. And so the nice thing about a roller is what the roller does is it only gives you a reaction force in the Y. So if they were both pinned, it would be indeterminate. In our case, it isn't. So we're good to go. But that's one of the things you'll notice, right? Because if I had an extra arrow here, I would have 4 unknowns and only 3 equations. And since this is statics, not mechanics materials, I wouldn't be able to solve this. You know, the only way I could solve it is if I kept into account like the sag and the this and the that, and internal forces and stuff. So for our purposes, you're going to see all of these are pretty much going to be pinned and roller, pinned and roller, pinned and roller, which is good because you can kind of get into the swing of things. So the first thing is if you're going to analyze this truss, you've got to be able to identify all the forces. We're also, and I think I put this in a different video, we're going to assume the links are weightless. So it'll specifically tell you if they're not going to be weightless, but in our case, we're going to assume they're weightless for the moment. Makes the math a little bit more straightforward. You're going to identify, so like I said, you're going to identify all the forces. So the 500 Newton would say be given. So you would need to come in here and say, I guess I'll call this little area, I'll call this A, B, and C. I'll call this one C, and up here is B. Okay, so we've got A in the X direction reaction force, an A in the Y direction reaction force, and a C. I'll just write that C instead of CY. I guess the problem also would have had to have given you some distances, so I'll give these two as 2 meters and 2 meters. Ah, come back. Why did you do that? You silly thing. So 2 meters and 2 meters. Okay, so so with the method of joints, basically the idea is we can kind of break this out. So let me show you what this would look like. So I'm going to do this once insofar as teaching you all method of joints, but then after that, you don't really have to draw it all out again. So if we kind of start looking at like pin B, okay? So we can say, okay, so we've got pin B and we've got the link A to B. And then down here, I've got the pin also. Down at A. Then I've got this, actually I'm going to probably need to draw these a little bit further apart. So I've got this roller here. Then I've got another link. And then I've got another, sorry, that was the pin. This is the roller. Roller, not ruler. This is the roller. And then I've got this connector here. That doesn't even sort of line up. Oh, drawing is hard. There we go. Okay, so those are all the parts if I wanted to kind of break them up. Okay, so I'm going to go ahead and I'm going to draw all the external forces that I would have had on the original drawing. So basically I'm breaking this out, and right now I'm just going to put on the external forces, but in a minute I'm going to label the internal forces. Because really that's what we're going for. If we want to know if if something is in compression or tension, we really need to know what the internal forces are. So I can't analyze the whole thing as a system. I've got to break it apart. So first of all, I've got this 500 newtons, okay? And I still have these external forces, the AX and the AY and the C. So I can go ahead and label those. Let's see, okay. So I think I said in another video, I'm gonna assume everything is in tension, and then if it's not, I'll just get a negative, and that way I can just always associate a negative with compression. So I'm going to assume that this beam is in tension here, okay? Now, if this beam is in tension, remember that for it to be connected to something, that I have to draw an equal and opposite reaction force, an equal and opposite force. So if I'm going to call this tension AC, so each one of these arrows is tension AC, then that means if the whatever thing is in tension, then it's also going to be pulling on the pin in that direction. So this will also be tension AC. See, I need a bigger picture. There we go. So again here, if this thing is in tension, it's going to be pulling on the pin. And that's a little bit hard maybe for some people, not even for some people, for most people to kind of picture. So again, the idea is if you're pulling, if this is in tension, it's tight, okay? It's being pulled on. So in order for it to be in tension, it's actually pulling on the pin for it to stay in tension, okay? And maybe the way to think about it is the opposite, because maybe the opposite makes more sense. If it was in compression, it would be pushing on the pin, right? Because if you've got something, let's just pretend I got a giant post and I'm pushing on the post is in compression, so that means it's pushing on the pin. If I was going to draw the pin that it's connected to, it's pushing on the pin, so the pin is pushing back on it, so it's in compression. Does that make sense? I feel like the compression thing almost makes more sense than tension, so I'm going to say that again, just in case it helps. So let's say I've got a giant pole here and I'm pushing on it with some kind of force. Now, when we think about it, we can say, okay, well, clearly if it's connected to the ground, you know, in some way, then it's getting pushed onto the ground. So basically what's happening is the ground is pushing back. So these two forces are the same. So these are the equal and opposite Newton's law thingies going back to each other. But so that's why when you have something in compression, you're drawing the arrows in. And then whenever you draw something in tension, you're drawing the arrows out. So again, if I'm pulling on it, again, maybe we can do this. So if I'm pulling on this tree or whatever, then the tree, you know, you can say, oh, okay, well, it's also pulling out of the ground, which means that the equal and opposite force on the tree would be this way. So it's, yeah. So you can kind of see now that maybe it's in tension. But basically the idea, if it's coming out, if it's leaving, then everything's in tension. And so not only do we draw the arrows in tension on the bars, but we also draw the arrows in tension on the pins. So the pins are also in tension, if that makes sense. All right, so similarly, if we're going to draw this beam in tension, so we're going to do this and draw this beam in tension. So this is beam tension AB. So this is tension AB. So that means that over here, we've also got an equal and opposite force, tension AB. And down here we have an equal and opposite force, tension AB. Now it's really important that these are all labeled the same thing because we're in statics. So everything and internal forces are all going to be equal and opposite. It's beautiful, it's wonderful, it's inextensible. And again, inextensible is really important. So since it's not stretching, those forces are the same. If you're in a situation like in mechanics materials where things could be stretched or compressed or something like that, then all bets are off. But for the purposes of what we're doing right now, this is great. Same thing here. If we're going to draw this in tension, this will be tension B to C. So again, tension B to C. And since it's in tension, its equal and opposite force here and its equal and opposite force here are also going to be tension B to C and tension B to C. Now, the way that you know you've done this right whenever you're dealing with internal forces is if I combine these two together, if I combine, not these two, but if I combined all of these together, what you're going to see is everything, I was going to say everything I have in red, except I unfortunately have this in red, so we'll pretend this is in blue now. Everything that I have written in red is an internal force. So it's an internal force, and it cancels out if you reassemble. All right, so the idea is if I took, let me see if I can do this without totally screwing up my picture. If I took this and I reattached it here, those TABs would cancel out and they would go away, okay? And the same thing here. If I move this down here, the TABs would cancel and go away. And the same thing, if I took, come here, why are you moving all over the place? You're very sensitive this morning. If I took this and I moved it here, those TACs would go away. And if I moved it here, those TACs would go away. So again, the idea just being that, come here, girl. As I move this around, if I reassembled the whole thing, I'm gesturing out in space like y'all can see me, but if I reassembled everything, then all of those internal forces would cancel out and we would end up with just what we had in the original picture, which is just those 4 external forces. So again, the external forces that we had are 1, 2, 3, and 4. So those are the same forces that we had. Everything else has equal and opposites, and they all cancel out. Okay, so that's kind of like the long way of getting started. And as long as you understand it, you do not have to draw this picture every time that you work one of these problems. But what we're basically going to do is, instead of drawing this picture out every time, what we're going to do is we're going to focus on just the individual joints. So basically what we're going to do is we're going to take this picture, and this picture, and this picture, and we're going to deal with each one of those 3 joints separately. Okay, and then we're going to draw out the joints, and then we're actually going to be able to figure out all of the unknowns. Okay, so let's start with node or joint B. So we're going to start with joint B. Okay. So if we go here, we'll start kind of fresh, a nice fresh piece of paper, digital paper. So if we start with joint B, all right, so joint B, we've got the 500 newtons that is known, and we have the tension AB, and we have the tension BC. Now, I think if you remember the original picture, this was a 2 meters and 2 meters, so that means we've got a nice little 45-degree angle here. So that's good. So we can go ahead and we can do this. Now, something important to note, one of the reasons I started with joint B, let me go ahead and draw the other ones out just so we can kind of see. So joint A, I can at least tell you why I didn't start with joint A, because starting in the right place really does save you some time. So if I start with joint A instead, I have this TAB, TAC, A sub Y, and A sub X. I'm just drawing them in different colors to make it consistent. I always think that that helps, but you definitely, don't worry about that. So TAB and TAC. So in this particular one, right here I have 2 unknowns. And you're like, well, I have 2 unknowns, 3 equations, so I should be totally fine. Actually, you're not going to have 3 equations, and that's where I'm going to get to. So I have 2 unknowns, but I know that I can solve something with 2 unknowns. This has 4 unknowns. And I should theoretically know going into this that in statics in general, if I'm in 2D, all I can get is 3 independent equations. So for 4 unknowns, I already know that that's a non-starter. I couldn't start on joint A even without thinking about that one too hard. But let me look at joint C. Okay, and I'll show you why you can't actually start there either. So at joint C, I had just the regular C, that force in C, and then I had tension in AC, and I had tension in AB, or sorry, BC, and tension AC. Now, this has 3 unknowns, and actually I cannot start here either. Because, okay, you'd be like, all right, but I have some of the forces in X and Y and some of the moments, which is great, except, sure, we could do some of the forces in X, and we could do some of the forces in Y. But if we wanted to do the sum of the moments about, say, the only point we have, which is C, what are you going to do? Because there's no distances. And you're like, well, I have this like 2 meters over here, but no, none of that. In this picture right here, there are no distances at all. So I actually can't do any moment equations. So if you hate moments, this is like the perfect section for you, because, or joint, this is the perfect thing to do because there's no way to take a moment, because everything is, whatever you would call it, everything is not even collinear, everything is coincidental. It all coincides on one point. So you can't take the moment about anything because there are no distances. So this is actually like in the Hibbler book, it's like the chapter 3 problem. So actually we could have theoretically solved this problem like 2 or 3 chapters ago because we didn't know how to take moments. And so, but we waited till now because, you got to have something fun to do later. You can't do all the fun in the beginning of the class. So again, 3 unknowns is actually too many. So whenever you're looking of where do I start, you want to start with something that has just the 2 unknowns. Okay, and from here it's actually not too bad. We're just going to start off and do the sum of the forces in the X and the sum of the forces in the Y. Personally, I'm probably going to start out with the sum of the forces in the X just because I can kind of see how this is going to play out. This requires me to do less work. So I have the 500, and if I break the TBC out, it's going to be the square root of 2 over 2 TBC. That's the sine or the cosine or however you want to view it, but plus square root of 2 over 2 TBC, and that's going to be 0. which means that TBC, now they're both positive, right? Because if I break this out, I don't want to mess up my picture, but if I break this out, the x direction is in the positive x direction. It'll be in the negative for the y, but they're both positive here. So that means that TBC ends up being negative 707, which means it's in compression, because remember we said that everything that we draw, when it turns out to be negative, is in compression. Now, if you look at the original picture, that maybe kind of sort of makes sense, because if I'm pulling on this here, this is going to get smushed, right? So if it would be the one that would crumple. So you think, well, if I pull here, that one's going to crumple. It's probably in compression, and in fact it is, because I got a negative number. Okay. And then for the sum of the forces in the y direction, I've got negative TAB, and again minus, because this component, again, like we said, this component is also in the negative direction, minus TAB minus square root of 2 over 2 TBC. And this is where you got to be careful to make sure that you're doing your math right and not doing something dumb with a negative sign. So TAB is going to be equal to, why is it jumping all over the place? TAB is going to be equal to the negative square root of 2 over 2 TBC. But remember that TBC is negative. So whenever I plug in that negative sign, then it comes out to be a positive. So TAB is equal to 500. And so that means it's in tension. Okay? Got it? So again, if you look at the original picture, the idea is if I pull on this, particularly, then this one is going to get stretched out as it tries to kind of, keep it back where it's supposed to be. So that one's going to stretch. So it's in tension, which should make sense. All right. So we have those. All right. I'm going to make this a little bit smaller so I can fit this all here. So now let's take a look at joint A. For joint A, let's make sure that we can solve everything. So we used to have 4 unknowns, but now I know TAB. But yeah, I don't know TAC yet. I think I'm missing something. So let's not do that one, because I think I still have 3 unknowns. So let's skip that one. So we got the 4 down to 3, but we need to get it all the way down to 2. All right. So let's go ahead and go over to joint C. 3 unknowns, but now we know TBC. So that means that we're now down to 2 unknowns. All right. So again, we're going to take the sum of the forces in the x and the y direction, and whichever one you want to start with, it doesn't matter, especially in this one. I think they're both going to work out just fine. So again, if we break out TBC, square root of 2 over 2 TBC in the positive direction, you're like, but it's negative. I know, but the arrow is in the positive direction, so stop asking questions. Don't question me. But no, it's sticking up. So wait, I'm just arguing with myself. That was funny. Okay, no, so it's clearly in the negative direction. Science is fun. I was in the y already. I was thinking of y, because it was just silly. So, okay, let's try this again. So it's in the negative direction. So we have a negative x component. All right, let's try this again. So the TBC has a negative x component, and the TAC is also a negative x component. See, this is what happens. You get overconfident. You're like, I can do math, and then you stop paying attention. And this is how sad homework days happen. All right, so TAC is going to be equal to negative root 2 over 2 TBC, but again, TBC is at negative 707, which means that I'm still giggling at myself. I crack myself up. I'm so funny. So TAC is going to be 500 newtons. All right. And again, I don't know why I'm boxing these in all of a sudden, but this will be in tension. So you can just say T for tension if you want, or not. But this is in tension. And then we'll also look at the sum of the forces in the y direction. Really, this is an organizational problem. Once you get it set up, it's just doing the math right. Shockingly, if you can just do the math right, you'll be fine. So as I was trying to say before, clearly TBC is pointing up in the up direction, so that's positive, and C is also pointing in the up direction. So that means C is equal to negative root 2 over 2 TBC, and we keep just getting the same number over and over, and that's because we have a symmetric system. So C is equal to 500 newtons. as well. I can't help it. I like to box in my answers. It makes me feel like I've accomplished something. It's like my favorite part. Okay, now we can actually go back and do joint A, because if we look, now I have TAC. So instead of having 3 unknowns, now I have 2 unknowns. Amazing. Okay, so I can look at the sum of the forces in the x direction. This one's actually really kind of straightforward, so I'm glad I left it to the end. So sum of the forces in the x, TAC is in the positive x direction. AX is in the positive x direction. So that means that AX is equal to negative TAC. So that means that AX is equal to negative 500. So this is neither in compression nor tension. This is just means that we drew our arrow the wrong direction, because we don't really talk about a joint being in, I guess you could talk about a joint being compression or tension, but in any case, in the x direction, it's getting pushed on. The joint is getting pushed on. Then some of the forces in the y, TAB is drawn in the positive direction. AY is drawn in the positive direction, so AY is equal to negative TAB. So AY is also equal to negative 500 N. All right? Yay! Okay, now I know that this video is going on for a really long time, but there's actually another way that you can solve it. So I'm not going to solve it the whole way that way, but let me just show you another way you can do it, just so you know that it's out there. So another option, and you guys are doing so good. Way to still be paying attention. I am impressed. Candy for everyone. Go get yourself some candy. You totally deserve it. So remember that we can still examine the structure as a whole. So if I just kind of look at what the basic thingy looked like with the AXAY and the C and the 500. So I could still do this, and like I said, I'll just go ahead and label it out. AX, AY, C, and these distances were 2 and 2. I know you're tired, I'm tired, we're all tired. I can still analyze this structure, so I could still do, all right, I'm going to do the sum of the forces in the x, so that's AX plus 500 is equal to 0, so AX is equal to negative 500. I can do the sum of the, I can't do y yet, but let's go ahead and do the sum of the moments about, say, A. That's going to be the 500 times 2 is going to be negative 500 times 2. And then the plus C times 2, which means that C is going to be equal to positive 500 newtons. Okay? And then I can do the sum of the forces in the y, giving me AY plus C is equal to 0. So AY has to be equal to negative 500. So now I've gotten all of those external forces. Then you can go, let's say, inside to solve it. So if you already knew A and C, the two A forces and the C force, you actually could have gone straight to here and solved that one and gotten TAB and TAC a little bit more quickly, maybe because you had the 2 green arrows, so you could find the 2 red arrows. So if you're in a time crunch, maybe that would be a little bit faster. It just kind of depends on whether or not you can easily solve for these. Well, that was given, sorry. But it depends on whether or not you can actually solve for these. So if you can, great. And you still can do that. And then you can go inside and draw the joints and do all of that. But just so you know, either way is an option. You just kind of go with whatever will get you to the answer you're looking for the fastest.